Okay, well, last presentation of the day. So I've got a water pistol hidden down here. So if I see anyone falling asleep, you're being forewarned. My name's Bruce Ashcroft. I work for Multiconsult in Norway. And today I'm going to present an example about grouting in rock. And some of this is based upon the earlier work which Louise did. Just before I start, has many people here worked with grouting in rock before? You see a show of hands? Okay, a few. I can mostly make it up. Brilliant. Right, to begin with, I'm going to talk a little bit about the grouting that's been done on the Fornebu Metro Line project that I've been working on for the last 5 years. And then afterwards, I'm going to talk through a bit of Clause 13, groundwater control in Part 3 of the second generation of Eurocode 7. So just a little bit about the project to begin with. Fornebu Metro Line, so it'll basically be a new metro line in Oslo, Norway, from the centre of the city down to the southwest. Designer is PGF, so a joint venture between Multiconsult and Covey. Line was first suggested in 1919, so it only took us 101 years to start building it. Length is just shy of 8 kilometres. There'll be 6 new stations and construction's ongoing at the moment. You can see, like with most similar projects being built now, BIM is the project's main information platform. You can see here one of the shafts at the stations after being excavated, how close it is to what we had in the model, which is always useful. And the total cost is about 2 billion euros. Okay, why do we grout tunnels and portals in this case, which we're going to focus on? The first reason maybe is to avoid unacceptable damage to buildings and other infrastructure. So although most of the project is excavated through rock, over the project we have a layer of marine clay of varying thicknesses, where if we lower the groundwater table there, we can have potential for quite a bit of settlement, which can damage both buildings, infrastructure and nature. Also important is to meet the functional requirements of the tunnel as a structure. Obviously, if you're going to get the metro in the morning, you don't particularly want to be using an umbrella before you get in the train because there's water leaking in. Lastly, too, to reduce pumping costs. Now, this might not seem like a big thing, but for example, if we have some undersea tunnels in Norway where it hasn't been grouted adequately and we had lots of water which went into the low points, and a few years ago where we had very high electricity costs suddenly, it was a very significant amount of money that had to be spent every year to pump the water out. Okay, so a bit on monitoring and environmental considerations for the project. So on the project, we have a general target for water infiltration, which is less than 4 litres per minute per 100 metres of tunnel or underground opening. And this is irregardless of how large the opening is. And we have openings up to 320 square metres in some cases. So a couple of years before the construction started, we started with continuous monitoring of groundwater levels using piezometers. And additionally, we're using INSAR measurements with satellites for ground settlement monitoring in close collaboration with another nearby project. You can see here some of the points along the alignment of boreholes and piezometers. Okay, a little bit on the vulnerability and risk analysis here. So, as I've said, for the whole project as a whole, we have an aim, a target which we need to meet of less than 4 litres per minute per 100 metres. But what we did beforehand as a designer was that we looked at the alignments and split it up into different vulnerability classes. Now, if you have a section of the tunnel where you have, say, 40 metres of overburden and it's just rock, and you have very little infrastructure above it, then you would probably classify that as a green area. Now, that doesn't mean that you don't have to satisfy the target, but what that does mean is that you anticipate that less of an effort will be required in terms of grouting to satisfy that target. Hence, you might just have one round of pre-grouting with a Portland cement and or micro cement. In other cases, if you have a red section, this might be where you have very little overburden, lots of soil lying over the rock, lots of potential for damage. So there you would anticipate that you need to have a very intensive grouting effort. This shows one of the stations here with the fans and the grouting geometry. Okay, just very quickly now, just different initial procedures for the different vulnerability classes. And all this shows really is that this was just purely an initial plan, as it were. And all it shows is that basically the higher the vulnerability class, the more grouting is anticipated to be able to satisfy that leakage target. Before we go into clause 13 in detail, I just wanted to talk a little bit about performance-based grouting versus requirement-based grouting. So performance-based grouting, basically, this is where you focus on achieving a specific performance criteria. So in our case, less than 4 litres per minute per 100 metres. That doesn't mean that you don't start with the procedure, you do. But what it does mean is that if you do not achieve your aim of getting your leakage below that criteria, then you have to be able to have the flexibility to adjust that procedure. Whereas a requirement-based procedure is a lot more rigid in that you start off with a procedure, which you would do for the performance-based one anyway, in terms of centre-to-centre distance for the grout holes, the length of the grout holes, the pressure that you pump in the grout at, the grout mix, the packer placement, for example. And that's sort of quite a rigid plan that you sort of stick to. We'll come back to that a bit later on. So just very quickly then, the design case description. So groundwater control by cementitious grouting, typically. We also used colloidal silica in some areas. The ground's Cambro-Silurian rocks, typically limestone and shales with some igneous volcanic dikes. Geotechnical category 3, mainly verified using the observation method. The calculations being analytical, and cement grout design having not been described in the previous Eurocode. Okay, so a bit on the actual portal itself. So this is the beginning of the adit tunnel. You can see here. What was interesting here was that there was actually an existing tunnel which was built during the Second World War as a sort of emergency tunnel to hide in during bombing. You can see a longitudinal section here where this tunnel, which was eventually concreted in. You can also see there's a retaining wall up here with some bolts used to support it. You can see the portal surface here in rock. We've also got some water pipes here and other service cables underneath. Another thing worth noting here is that along here, Lilleakerveien in Oslo, there was one of the most significant weakness zones in the area. So it was extremely poor rock conditions, particularly up where there was very little overburden. There's about 3 metres overburden here to start with. So this just shows a very simple overview of what the fan geometry of the grouting fans look like to begin with. The groundwater level we knew was here from where the water had pooled after being left over the summer. So this shows the geometry of the grouting fan. And this is a table which Adrian showed a bit earlier. We're into clause 13 now of part 3. This would be a class 1 where we call it an impermeable barrier. Even though it's not impermeable, we think that 4 litres per minute per 100 metres is such a low value that it's considered to be impermeable. Ultimate limit states, just quickly, this isn't actually given in the code, but this is an interpretation. So ULS, so you can have failure of the ground itself where you actually jack the ground open. Some people maintain that that's actually a good thing and that you actually fill some of the cracks by doing that. Again, different philosophies of doing it. And obviously failure of the packers, which no one would argue, I hope is a good thing. SNS, discharge of grout into surrounding buildings, limiting value of leakage per area, and heaving of the ground. So obviously, if you don't grout enough, there's a high likelihood that you will have settlements, but often if you grout at too high a pressure, then there's even higher likelihoods that you'll have heaving of the ground. Ground investigation. So here in clause 13, there's a long laundry list of things which should be provided beforehand. Often lots of this information is already available from other projects and previous stages of the project. Prevention of water flow. So we get a long list here of different sections. As I said before, the project, geotechnical category 3, so when looking at monitoring, and again, this comes back to performance-based grouting, where we need to monitor to make sure that we are actually achieving the goal that we have. So obviously you can have V-notch weirs in the tunnel to actually measure how much water is coming in, particularly the measurements are usually taken after a long weekend or a break in the construction activity, so you don't get any of the water from the construction activities. That's just what's leaking into the tunnel. Obviously, piezometers, we have hundreds of those which are checked weekly. Ground settlements, satellite data, and they're in the tunnel itself, control holes and lugen testing. So depending on the vulnerability class, if it's 3 or 4, there you have systematic control holes to check that there's no water coming in. And if there is, then obviously you need to take a new round of grouting. Okay, this section on testing here, it's fairly brief, to a few more questions than answers here really, but how often should these tests be carried out? Should it be for every grouting hole or every grouting operation? Is it a rising head test? Good old bucket to collect the water, or lugen testing? Reporting. So this is a very comprehensive section here. Again, seems to be more valid for requirement-based grouting maybe than actual performance-based grouting, as this seems, at least my interpretation, is that this would lend itself to where you have quite a rigid sort of procedure that you follow for your grouting, and not one where it can be, it can sort of ebb and flow depending on what sort of results you're achieving. Okay, so just some conclusions from the earlier task group B1.8 study. So in terms of ease of use, anything could be better, but the code is quite general here. But on the plus side, that means that it gives it some more, gives one more flexibility when working, and it can obviously refer to the National Annex for guidance. It does seem to me to be more suitable for requirement-based grouting rather than performance-based. One thing, the impact of surroundings, that's really a critical part of groundwater control for grouting, and this clause doesn't really cover it. And that can obviously be in terms of settlements and buildings and infrastructure, but also in terms of, we had a river quite close to that portal with these volcanic dikes which go through. If you get connection with those, the grouting mass can easily travel hundreds of metres as it takes the path of least resistance. So that means that you have a really large potential zone of influence around where you're grouting. But it's very good that groundwater control is given its own clause, which means it's always on the agenda, as it were. So, as I said before, an advantage generally is the code allows the designer quite a bit of freedom to handle the problem as they see fit. The cons are that the general code means that there's no sort of lowest bar set for the calculations. Okay, and so just final thoughts. So it's no use saying we are doing our best. You've got to succeed in doing what's necessary. Winston Churchill. And obviously, again, this comes back to the performance-based grouting, that you need to get the job done, And it's no good just saying we'll follow the procedure. That's all we can do. Anyone that's been involved with post-grouting knows it's an absolute nightmare, and it's yeah, it's let's not finish on that note. But yeah, yes, thank you.